So yeah, let's get started. So welcome everyone to the CPPC seminar. So I don't really need to introduce our speaker today. You all know Markus, but for people who don't, Markus is a PhD student here at Sydney, being supervised by Salim Bohm. Markus is now approaching the end of his PhD. He's currently writing up his thesis, and as a tradition around here, we like to give finishing PhD students some extra stress by forcing them to do a seminar, which is what Markus is now doing. So welcome everyone, those in the room and those online, and I'll leave it in Markus' hands.
Okay, so yeah, welcome to my talk. Some of you may have heard parts of this before, but today you're getting the long version. So essentially, to give a quick overview of what I'm going to be talking about is first, I will give a quick intro to dark matter, what it is, why we're interested in it, and so on and so forth. Then I will give a brief introduction to the sort of test case model we are using for our various analysis of dark matter interactions. Then I will present the novel type of constraint we have developed using gravitational waves. And finally, I will add some other supplementary constraints to this type of model from cosmological data. And of course, I haven't done all this alone. So thanks to collaborators, and for anyone wanting to read the papers, they are right here as well. So what do we actually know about dark matter? Not a whole lot, some might say, but we do know that there is quite a lot of it out there in the universe. We also know that they have either zero or very limited interactions with the standard model of physics, particle physics, because otherwise we would have detected it in some of all the various experiments we have made to detect it. And then, of course, we know it clusters gravitationally, at least on relatively large scales, which is how we know it exists. So essentially, we do know a lot about what dark matter is not, but we don't know a lot about what dark matter actually is. So what can we learn from gravitational waves? So there's also a few ways we can learn more about dark matter, which I will not, most of these I won't cover very well. So there's, of course, laboratory experiments, such as direct detection experiments, where you put up a big tank or target of some sort, have some very sensitive detectors, and you hope a dark matter particle comes in, hits the thing, the detector goes bing, and you've seen dark matter. Most people claim that their detectors do not see dark matter, so no luck there. Then there's colliders, where you smash particles very hard into each other, hoping to create new particles, and maybe if you have particles of dark matter, some of the particles coming out would be dark matter. You would see this as missing energy because they would not be picked up in the detector, and yeah, again, no luck. So we do know that dark matter is somewhere out in space, and we can look at astrophysical signals to see if we can find it. So again, we have what's called indirect detection, which is essentially if the dark matter is doing some sort of interaction with standard model particles that causes radiation or other particles to be emitted, maybe we can detect those particles and we can detect sort of more of them coming from area with lots of dark matter, such as the galactic center. We have sort of see some excesses above what we expect and so on, but nothing conclusive that says, hey, this is annihilating or decaying dark matter. Finally, which is what I will be focusing on today, is structure formation. So different dark matter models predict different ways structure will form in the universe. And so by observing the structure, we can at least rule out some dark matter models that would, well, cause different structure formation. So in the early universe, everything was very homogeneous. We had these tiny little perturbations, but they were small. And baryons, that's normal matter, they were strongly coupled to the photons, and the photon pressure prevented these baryons from collapsing to form structure, but instead you would essentially have pressure waves outgoing from where the overdensities were. And if we go into Fourier space, we see this as oscillations, and that's what we see in this little figure. We see the baryon acoustic oscillations here, which continue until the photons and baryons decouple, where baryons are now allowed to form structure and photons just free stream away and become the CMB. Non-interacting dark matter doesn't feel this sort of pressure, and thus can start to form structure much earlier than baryons, and thus form the seeds of all the structures we see in the universe. That all changes if we let the dark matter interact. So if dark matter interacts with light particles, or like photons or neutrinos in the universe, it starts looking a lot more like what the baryons are doing, delaying structure formation, suppressing structure. So there's different types of model with suppressed structure. These come about in different ways. So maybe the simplest one is warm dark matter. You don't have to have any funny interactions. You just need to make it a bit warmer, so it free streams a bit more, like neutrinos, but not as much. So this is allowed for thermally produced dark matter at masses down to a few keV with current constraints. These essentially don't form structures that are smaller than the free streaming length of the dark matter particles, because they've free streamed away from such structures. Then we have ultralight dark matter, which is behaving wave-like, and quantum mechanics effects and so on, and therefore they are not allowed to form structures due to these quantum effects that are qualitatively different from other types of structure suppression, but at the same time, lead to suppressed structure at more scales. Finally, we have interacting dark matter, which suppresses the small scale structure. Well, it looks similar to warm dark matter, but the mechanism is different because you have sort of a scattering length. So you get damping length. You can't really form structures that are smaller than the scattering lengths. So we are going to be focusing today on dark matter neutrino scattering. So this is a good baseline model to look at this from, because we don't need to touch any baryonic or photon physics, as the neutrinos interact so weakly with everything else that it's not going to affect. And then, as a sort of theoretical justification, there's a bunch of open questions about neutrinos. For instance, how do they get their mass? So there's definitely something going on there. Maybe not something we're going to discover, but something we can exploit. So for simplicity, we're also just assuming velocity independent scattering cross-section, similar to Coulomb scattering. So if we evolve this linear, linear evolution is good to describe the early universe because, as we mentioned before, these perturbations are small. So we can describe the early universe well, and we can describe large scales well. And this gives us things like the baryon acoustic oscillations or CMB predictions, and can be used to provide the initial conditions for the nonlinear simulations that are needed to describe the later universe. So I don't normally like putting equations on slides. I'm not going to go into depth with these. I'm just showing you these, so we can see the black is just the normal non-interacting case, where when we add this interaction, we get essentially scattering of the neutrinos, a scattering term for the dark matter. We find that for this cross-section, the rate happens as p squared over e squared, and then all these standard terms. And then we parameterize our interaction strength in terms of this U parameter because of the degeneracy between the cross-section and the mass of the dark matter particle. This degeneracy is essentially, it's because if you have a large cross-section, you get more scatterings, right? If you have a lighter dark matter particles, you need more particles to make up the density of dark matter, so you get more scatterings. So you can't really tell whether the dark matter particle is larger or the cross-section is larger. So in the end, this is sort of lifts this degeneracy and just lets us constrain this parameter instead. So yeah, as I mentioned, all roads lead to Rome. Everything gives you a suppressed matter power spectrum, where we can see that both dark matter neutrino interactions, warm dark matter, and action-like dark matter give you this characteristic suppression of the dark matter, of the matter power spectrum at a given scale. They might be qualitatively a bit different when you look at them, but they all can essentially give you, yeah, the suppression at some scale if you just tune the values to match each other. And this is also true for other interactions, such as interactions with massless neutrinos or photons, all the same thing. So this model that we are looking at also got a little bit more interesting recently, because a different group was using our model and seeing could we constrain it through Lyman alpha observations. And what they found was a hint, I would say, of a preferred model versus standard cold dark matter. So this is the posterior distribution that is very clearly peaked away from zero for interaction strength. Of course, I'm not going to say I believe this is the right model, but I believe this is interesting and warrants further investigation. So their preferred value is about 5 times 10 to the minus 6 and has an upper bound of, yeah, around 10 to the minus 6. So that's 2 orders of magnitude smaller than we obtained from CMB and BAO analysis.
Do you know if they considered the models you just had on previous slide, like the ultralight axions and stuff like that?
I don't think so.
Is there anything specific about that model?
So I think the analysis they did was only specific to that model, but they mentioned that there were some funny things about Lyman alpha signals. So it's very possible that you would get the same, but they didn't do it explicitly. So how do we get from this interaction to gravitational waves, you might ask? So when we suppress our structure, we get less or delayed galaxy formation or formation of progenitors of galaxies. This means that we get less star formation or later star formation. This means we get fewer or delayed formation of the black hole binaries that come out of binary stars. And finally, this gives us fewer black hole mergers to detect. And looking at this, we can make our little software pipeline to predict our signal. So our basic input is this dark matter neutrino interaction strength, which we put into the Boltzmann solver class, which we have modified to include these dark matter neutrino interactions. What we have then done is that we have then taken the output of class, run it into the n-body code gadget to calculate our nonlinear evolution, and specifically to get the halo mass function. And we also take the linear power spectrum from class and put into the galaxy formation code galform, and then we cross-check the halo mass function galform produces against what we have from gadget to ensure that it correctly captures what the model does. And the galform then uses a Monte Carlo method to generate a population of galaxy and the redshift history, giving us the star formation rate density, the metallicity distribution over cosmological times for this population of galaxies. What we can then do is we can put this into the code compass that then, based on this, generates a population of binary stars, evolves them, binary black hole formation, and does this evolution saying, when are these going to merge? How big are they? Blah, 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 giving us essentially a black hole merger history for the universe. And the question is, can we detect this, and can we see a difference between lambda CDM and our interacting model? So there are some hiccups when it comes to simulating suppressed structure, namely the fact that when you put this into an n-body code, because you have a finite number of particles corresponding to 10 to the something solar masses of matter each, if you have too little structure, they start to artificially, what they call artificial fragmentation, which creates these spurious mini halos on very small scales. So you see that as when we compare these two box-sized simulations, that you get this additional low halo mass upturn, which is moved to smaller masses if we use a smaller box with smaller mass particles, which is not present until we get to very small scales with our non-interacting model. Thus, we can't really just take our direct simulation output and put it into sort of post-processing code to assign galaxies to our halos, because how do we know which of these halos are spurious, and how do we know which of these halos are real? Which is why we use the galform Monte Carlo method of generating galaxies, because then we know all our galaxies are real. So what we've done to ameliorate this problem is that we have simulated a bunch of boxes and of different size, and then we've cut off the halo mass function once it starts to get iffy, and then we've just stitched the parts together that we can trust, essentially. So as I mentioned, we need to avoid this, so we tried to find an analytical way of describing these halo mass functions. And so what you see here in simulation are our stitched together halo mass functions normalized to the cold dark matter one. So we see a suppression, and if we just put this into the standard Schaff-Tolman formalism, which is a halo model that should be able to calculate our halo mass function from the linear power spectrum, we see that the slope doesn't quite match. And so what we do is we've developed a new formalism for this suppression, where rather than inputting our suppressed linear power spectrum into the Schaff-Tolman we use a Schaff-Tolman based on the non-interacting cold dark matter one, and then we have this suppression factor that is then computed from the interacting linear power spectrum. So where we've fitted these alpha beta parameters to find out what works best, and then we've tested it with different interaction strengths to see that it's not just fitted to these three, and we find that this suppression works really well if we set so this beta means we use the mass corresponding to the mass of a halo corresponding to the K value, where the linear matter power spectrum is suppressed by 10%, and then alpha is fitted to 0.9. And yeah, as you can see, it fits well, and it fits as well as these fits by Lovell, which uses a bunch more parameters than we do. So that's cool. So how do we generate our galaxy populations is the next question. And yes, we use this Durham semi-analytic galaxy formation code called GalForm. Yeah, as I mentioned, we avoid this problem of artificial fragmentation by generating our populations directly using GalForm rather than running GalForm on a halo merger tree. And so GalForm uses this extended projector method, which to generate artificial merger trees without relying on n-body simulations. And these do reproduce the fitted halo mass functions that we got. So that's good. And what essentially happens is that we have our set of 0 today halo mass function, and then based on a probabilistic treatment, GalForm asks, okay, so in our next time step, what's the probability that this galaxy was produced by a merger, and which two galaxies could have merged to form the galaxy that we have now? And then we go back to, in our next time step, if we merged, then our two progenitors, would they have been formed from a merger? Which two galaxies would they have merged from? And we do that for our entire population of galaxies today, and go back to until we reach the smallest progenitors that we want to track, which is the decision parameter in the set. There you go. So yeah, and this lets us compute the star formations, the metallicity evolution, etc., of these galaxies using sort of well-motivated astrophysical models that have been tuned, actually, well, not so much tuned. They're using good physics input, and they reproduce the observed galaxy populations well, and so on. So sure, you can change different parameters, but like there's a limit to how meaningful it is to change them too much, because we do know these physical processes happen, and we have a good idea of how strong they are. So we can look at what's the input, what's the effect on the galaxy populations of having our interaction. And what we can see is, sure, it depends on how strong the interaction is, of course. And what we find is that we can actually already rule out the alpha hint using only galaxy populations. So this is, yeah, galaxy population, the BJ band, that's some observational magnitude band, whatever. And we can see that even if we completely turn off supernova feedback, which is sort of the thing that would normally suppress structure growth, we are unable to reproduce the low luminosity galaxies. Instead we actually overpredict the number of high luminosity galaxies and then still underpredict down here. So there's just no way this model can give us the correct galaxy population. That's cool. We've already ruled something out before we even get to the main event. Then, yeah, for this we also try calibrating the parameters so we fit it as well as possible. And for the others, we've just used the standard lambda CDM parameters because they fit. We can reproduce the galaxy population well. So having reached the point where we say, okay, this will give us a correct galaxy population today. This is worth going further on. We can generate our compact binary population. So, as I mentioned, these compact binaries form from massive binary star systems. You have two stars. They are quite short-lived if they're going to end up as black holes. They're binary. You might, as long as they don't, throw their partner away, they will end up becoming maybe binary black holes. And so it's essentially a delayed trace of the star formation rate because, well, shortly after you form a lot of heavy stars, you're going to form a lot of black holes. So it's not completely that simple because there is dependence on the metallicity of the stars, where higher metallicity stars, if I remember correctly, are less likely to end up as black holes than low metallicity stars for a variety of stellar process reasons that I am not an expert in. But yeah, this is all described in all these COMPASS papers. And yeah, so COMPASS uses all these catalogs of star evolution, looks it up, what's the probability from, if we have this amount of star formation and we have this amount of metallicity, which stars are going to form, how are they going to evolve, et cetera, generating these populations, generating black hole merger rates. And yeah, so we get a binary formation rate that we can see actually is quite dependent on our interaction strength. So what we do find is that for the very early times, we had to go to slightly higher resolution in gal form to correctly capture it. So that's the difference between the dashed lines here and the solid lines, is that these are computed using slightly higher resolution for like slightly smaller progenitors in gal form. And so, yeah, higher gal form resolution will always push these curves up because it just means we're taking more stuff into account. But yeah, it's saturated here where lowering the resolution wouldn't really give us any more because the smaller structures don't contribute. So yeah, we generate our binary systems over cosmic time from the star formation rate and metallicity. And yeah, this is all computed from databases, computed from MESA, the sort of one of the state-of-the-art star formation evolution codes out there. And yeah, so we see a little bit of difference here between lambda CDM and our interacting model with 10 to the minus 8. It's not too big, but so yeah, but where with the lower resolution still, we can clearly see the difference between lambda CDM 10 to the minus 7 and yeah, 10 to the minus 6, which was already ruled out from the galaxy population, is just completely way off. Nothing going on there. That's oh well, yeah. So if we try to compare the formation of the black holes and when they coalesce, we get binary merger signal. That's essentially a time folding of the signal because you have some probability of when you form your black hole binary from stellar binary, how long is it going to live? And that has some probability distribution, and these are then just drawn from that. We do the time folding so that a formation rates that look like this for like a CDM and an interacting scenario will give us a merger rates that look like this. So it looks the same, but like slightly lower and delayed. So can we detect this difference today is the question. Sadly, the answer is no. These are the same models I showed the formation rates of earlier. This is the merger rates as a function of redshift. The problem is that with the current sensitivity of LIGO, Virgo, Cagra, we only really have a good idea of the formation rate around set of 0. And unfortunately, they all sort of converge around set of 0. They're all within this allowed band. What's really interesting is that we actually produce, for the standard CDM, something that's quite close to the upper limit of the allowed rate. So if we continue to decrease this and this allowed region, and we assume it's sort of converging on the middle, then maybe either our black hole formation model or lambda CDM could be in trouble. But yeah, that's still a ways away, maybe. But yeah, how about the next generation? LIGO, Virgo, Kagra, super great experiments, detect lots of black holes. What if we made some even more sensitive interferometers? So as this figure shows, like this current second generation interferometers can maybe measure up to a set of 2, and you lose some signal to noise if you go up to higher set, where the sensitivity of the next generation Einstein telescope and Cosmic Explorer would have a sensitivity that could measure this type of merger up to a set of 100, well before you would expect any of these black holes to even exist. So essentially, they would let us measure every single stellar black hole merger in the universe, which is pretty cool. And that's really what we need, isn't it? Because if we look at these, we see that the real difference in the rate happens at higher redshift. So that's where we want to look. And looks like we can do it. So we performed a sensitivity analysis of this set of next generation interferometers. And what we found was that for black hole total masses of between 10 and around 100 sum of the mass in the system, we will get signal to noise ratio above 10 for nearly all cases, up to 7 of 10. So we'll detect them, we'll see these guys. And then just comes the hard data science job of actually going through the data and identifying them and counting them and so on. But that's not my problem, at least not now. And what we did was we folded in the redshift uncertainty on these forecasts. So, the forecasted redshift uncertainty on these types of events, we folded this into our merger rate. And so this plot is, it's a little bit tricky. This Z star that we are plotting on the x-axis is the inferred redshift. Like, if we see an event, what redshift would we infer this at probabilistically if we take into account the uncertainty in the instrument? So we take essentially saying we're going to be wrong sometimes about the redshift, and then we're going to be measuring these redshifts. And then we're showing here on the y-axis is how many events are we going to see above an inferred redshift of Z star after, as I said, taking the redshift uncertainty into account of the instrument. And what we see is that the 10 to the minus 7 model and 10 to the minus and the lambda CDM model are clearly distinguishable. We're definitely going to be telling these two apart, where it's a bit more iffy about the 10 to the minus 8 model. What you see around here is the 3 sigma error bars, And if you zoom very far in, there's technically a difference between these don't quite overlap, but there might be more uncertainties that are not quite captured here, but this one should be quite clearly differentiated from this one. Of course, what you're going to say is, how about the uncertainty on the binary model? How do we know that we can tell the different uncertainties on astrophysical parameters for binary formation apart from dark matter interaction? And luckily we can, and I have plots to show you. So essentially the COMPASS code has a bunch of different astrophysical parameters that you can tune to different values, taking all sorts of things into account. What we have, so what you see here is, normalized to the fiducial astro model called dark matter, the rate of mergers as a function of redshift, and then with our 10 to the -7 fiducial astro model, one we are quite confident we can distinguish, and then with all these different astro parameters cranked up to like a significant deviation from the fiducial model. So we've sort of parameterized all of these in terms of sort of a linear parameter that takes the final output from CDM to the maximum deviation, and then we perform a Fisher analysis on these models, and essentially this tells us the confidence that we can distinguish an effect from other effects. And if the value here is small, we can say it has a qualitatively different effect from the others. And the important number here is on the diagonal, and particular interacting dark matter is different from all the others, which you can also sort of see on the plot, is that all of these lead to larger differences at low Z and smaller differences at high Z, where the interacting dark matter is essentially the opposite. So it would have a quantitatively different signal than if the astro parameters were just a bit different. So then we can compare and contrast this with warm dark matter. So if we run our n-body simulations with warm dark matter and with interacting dark matter, so worth mentioning here is that for all realistic values of the interaction parameter, the interaction will be decoupling like well before CMB times. So when you start your n-body simulations, you normally do that at set about 100 or something, much after CMB has been emitted. So there's essentially no interactions left at this point. You need to take the interactions into account in your initial conditions, which is very nice because you don't need to do a lot of complicated modifications to your n-body code. You can just plug in your matter power spectrum. So we did that for our interacting model, and we did it for warm dark matter. We did it for essentially two ways of modeling warm dark matter. One where we just take into account the suppression of the matter power spectrum, and one where we also gave it this velocity kick because it has a higher thermal velocity. And we thought the most thorough way to do this was doing both and seeing what the difference is. What we find when we evolve this is that at redshifts of 10 or smaller, these models are essentially completely indistinguishable. All hints of these characteristic oscillations that we saw in the linear matter power spectrum for interaction models, they're just gone. They are washed out by nonlinear structure formation. The upside of this is that any observation that would constrain warm dark matter can also be used to constrain interacting dark matter and vice versa at these redshifts lower than 10. If you recall our gravitational wave plot, we're looking at events at redshifts more than 10. So we can adapt these limits just as well to warm dark matter. So yeah, here's sort of an adaptation scheme with neutrino interactions, which interaction parameter corresponds to which warm dark matter mass, and to the same interaction parameters for photon interacting dark matter. So well, if we look at much higher redshifts, we see that these interactions, the oscillations imprinted by these interactions still exist, are still visible. So that's the redshifts of roughly 15 and higher. And we are fortunate that the SKA low instrument should hopefully be able to probe 21 centimeter hydrogen at these redshifts once it comes online in however many years, provided we give it enough observation time. So that's sort of, however, this is sort of still a rough estimate, because this is done with dark matter only simulations, no baryons and so on. So to do this, to like finally put this nail in and say we can tell the difference, we would need to do like proper high resolution simulations to actually get an idea of what the real 21 centimeter signal would be. But if it is able to distinguish the matter power spectrum down to a few percent, then it should be able to, at these relatively high values of K, it should be able to tell the difference between warm and interacting dark matter. So there's hope. So in conclusion, the next generation of gravitational wave observatories can be used to constrain suppressed structure formation, improving limits above what we currently have. Then SKA, when it comes online, will able to similarly constrain dark matter models with suppressed structure, and high resolution measurements of the matter power spectrum will be absolutely vital if we want to be able to tell the difference between different types of model that lead to suppressed structure. And yeah, here's a little overview of existing constraints and forecasts for the constraints. That's what I had to say today. So thank you very much for listening, and I'm happy to take any questions.
All right, thank you, Markus. Going to some questions from the audience. You can mute yourself, we'll be able to hear. It's the only one raising their hand or unmuting, so I'll go. You had a table where you map it onto the photon dark matter interaction case. And I guess this is basically just comparing the models where you have the same cutoff at this roughly the same scale, right? For the photon dark matter interactions, these the models which lead to suppression of that scale still allowed, because you can observe that presumably by observing the photons, like the CMB or something.
Yeah, so these will have significantly higher impact on CMB and baryons than this type of interaction would. So I don't quite remember what the limits are. But my guess would be that the SKA would probably still maybe improve the limits, but I would have to look that up.
Can I just ask a question? With the formation rates, you were showing them peaking around a redshift of, I think, between 5 and 7 from the compass models. Yeah. So it's reminding me of Dan Miles had a paper that showed the supernova rates similarly peaking, but I think they were peaking at later time. I'm not sure if there'd be a correlation there.
There's probably definitely a correlation. So, so as I mentioned, there's also this this metallicity dependence, where more metallic stars are less likely to become black holes. So if these supernovae form from more metallic stars slightly later, then they might have a lower probability of becoming a black hole, or more likely to be a neutron star, similar. So, but yeah, it might also just be that these are two different astrophysical models that don't quite agree.
What about like improving the galaxy count method? I mean, with future surveys, I know JWST or Euclid or something like this.
Yeah, that should also work.
Do you have a feeling of if it would be better than SKA or?
So I think the key thing about SKA is that we can probe much earlier times. What we find is that the difference between these interacting models is larger at early times, and then they essentially converge towards CDM the longer we wait. So the galaxy counts, and as we saw here, like all these models except for the 10 to the -6 are lagged by current galaxy counts. So you need to have some really high redshift galaxy counts, something.
And your these models that you have here, are these from your like earlier low resolution?
So both the low resolution and the high resolution lead to the same result here.
I guess my question is on so if there's an issue here, which is if you're comparing like the data to the model, there are fluctuations in the model which are actually larger than the errors on the data points.
Yeah.
So can that be reduced?
No, because this is, I think that they are probably Poisson errors on like the random number of galaxies we're taking. But so the resolution I was talking about is just about the smallest tracking. So essentially they would give exactly the same late time population of galaxies.
You could reduce some bridges statistics, presumably. You just had a bigger simulation.
Yeah, like but that's like a different parameter than the resolution parameter.
Yeah, sure, okay, but that's not a fundamental limitation of the method, really. It's just the resources.
No problem. I'm not the expert on this galaxy formation code, but yeah, I assume that if you just put in more galaxies, but then it might become infeasibly big to run.
Yeah, sure, okay. Anyone else? Let's see, anyone? So, well, let's finish the official